Let me show you how to solve conservation momentum problems. This is the statement of conservation momentum, and it's such a formal thing in physics. I feel like I should state this and maybe do a quick proof of it, right? But this is the notion: is that if objects collide, the net change in momentum is zero. And this is assuming it's an isolated system, or if we look at it right after the collision, right, from right before to right after the collision. Okay. This is another way to say momentum is conserved, or to say that if you add up the momentum of all the objects before and after a collision, it doesn't change, right? This is an informal proof, right? If you've only got two objects, let's make our universe very simple, right? If you've got object A and object B, right? The only way that A can change its momentum, right, is that B exerts a force on A, right, for some amount of time, right? So the change in momentum of A is going to be whatever the force is exerted on A, right, times some amount of time, right? And the only way that B can change its momentum is that there's some force on B, right, exerted for some amount of time, right? Okay. And then the second thing that's true is that these times, if A touches B and B touches A, they touch each other for the same amount of time. Try it. Try touching something for a different amount of time than it touches you. It just can't be done, right? And then the second thing is that, of course, the force on A is equal to opposite the force on B. This is what Newton's third law. For every action, there's an equal and opposite reaction, right? And then, of course, now we've got this notion that force A times delta T, right, just equals negative the opposite of, right? So if we add those together, if we go this plus this, the net change is zero. So equal and opposite forces acting for equal time cause equal and opposite changes in momentum. So the net change in momentum is zero. Is that a proof? I don't know. Probably not. Okay. Let's solve a problem. Let me just show you a problem here. We got Bob and Sally. Sally's running to the east and Bob's running, and it says collide, but really this is much more romantic than it seems. They dated in college. People thought they were going to get married, but they got busy with their careers, and Sally went off to France to work at the U.S. Embassy, and Bob worked diligently on his career in the States and found himself in Paris in springtime. And it was a very cold spring. The Seine River is entirely frozen and essentially a frictionless surface, right? And he sees Sally at a chance meeting on a foreign city street. The music swells, and here's this surface, and here's Sally, right? And she's running. She has no arms. Now she has arms, and she's running this way to the east. I'm going to make east be the right. Okay, and here's Bob, and he's running to the west, and they run toward each other and on this essentially frictionless surface that is the Seine River, and they collide. So we draw a little picture afterwards, right? It's more of a romantic embrace, right? There they are, and right? It's like love is in the air, and the question is, there's lots of questions we could ask, right? Like is a relationship, at this point, if they couldn't find time in the past to maintain the relationship, right? Oh, she doesn't have arms. Okay, are they going to continue the relationship? But the real question that we want to know is, what is the post-collision velocity of their entwined bodies, right? Okay, so to set this thing up, basically what you do is you decide everything to the right. I'm going to make east be positive, right? So west is going to be the negative direction, right? To the left. West will be to the left. Okay, here's Sally, here's Bob, right? 60 kilograms, 80 kilograms, right? She's going 4.5, right? And then his velocity, I'm going to make his velocity negative 2.3. Okay, this is important because if he's going to the left, we need to put the negative in there. These are all momentum is a vector, right? So we've got to put the minus sign in there. Besides, if he's got a positive velocity, that changes the entire genre of the story, right? It becomes like a horror story. She's chasing him, and he's trying to get away, but he's not fast enough. It's just a mess, right? Okay. Now, what we do then is we just set up the momentum, right? We just go m times v plus m times v equals m times v. The total momentum before equals total after, right? So we go 4.5 is our velocity, right, times 60. Right, plus 80 times negative 2.3 equals, and then if things stick together, if this is like, these guys are in this embrace, right, we can just say that they are 60 plus 80, right? You see people like out in the halls at Tualatin that are like that. We can just add their masses together. They never separate, right? And then that's going some velocity. So this is what you do. The formula, of course, for momentum is mass times velocity. So this momentum plus that momentum equals the sum of the momenta, right? Okay, so let's see, 60 times 4.5, this is 270 kilogram meters per second, right? And then 80 times negative 2.3, negative 184. So he had more mass, but he's going slower. It turns out he's carrying less momentum into the relationship, right? Does that mean he's less committed? I don't know. 140 times v, right? And then let's see, 270 minus 184, 86, right? And then I'm going to divide, okay, 86 divided by 140. And I get that 0.61428. 6 is what V is, right? Okay. Now we only have 2 sig figs, so we'd have to say V is 0.61 meters per second east, right? I know it's east because it ended up being positive. This was a positive number, yes? Okay. And positive was our direction that we decided east was, and west we made negative, okay? That's all there is to it. I think you need to draw a picture in these problems. I think this is the most important thing, is to read the problem, draw a picture. I always write the masses and the velocities right there because I'm a spaz. I just go boom times boom plus boom times boom equals, and then after equals separates before and after. I think it's simpler than energy problems, but maybe not. I don't know. I recommend doing a bunch of these example problems just because this is sort of like conservation of energy. It's something that you're going to get after repeating it for a while. So.